So now that we know what statics is, let's take a look at some tools that can help us analyze those things. One of those things is called a free body diagram. In science, you may have heard of a force diagram. They're the same thing. Free body diagrams, force diagrams. Let's take a look. So what exactly is a free body diagram? So it's a visual representation, in other words, a picture of forces and objects and how they interact. So here we have in the lower left, it looks like a truss. So it has some forces going vertically and some horizontally, but it's basically taking that part, it's isolating that part. So we know that there's some other supports here on the bridge, but it's isolating the part. Here we have a pulley that has some ropes or some chains, and then the weight of the pulley, and then here is a beam with a couple of, maybe there's two people standing on it. So don't really understand how to get there yet, but we will by the end of this presentation. So some of the free body diagram components, first thing is a force. And we remember we talked about in the static presentation what a force is. It acts in a straight line. It's a vector, so it has direction and magnitude. One thing to know about any vector really is with the direction and magnitude. Magnitude, it can be represented by number, or it can also be represented by the length of a line segment. So here you see green, for example, but if I were to draw a red arrow in the same direction, even though they're going the same direction, through the same angle theta, the red arrow is longer. So if by looking at this, I could tell that that vector, that magnitude is greater. And then the other thing we might see on a free body diagram is a moment. So recall that you can have a clockwise moment or a counterclockwise moment, and that a moment is essentially just a twisting force. And do you remember which moment is considered positive? So let's peel back the onion a little bit on moments and let's review them. We probably remember them, but let's just take a little bit to dig a little bit deeper. All right, so a moment is really just a force times a distance. And if we look at a wrench, for example, here we have a wrench with a force acting on it. It's got a point of rotation right in the middle of the nut, and it has a line of action. So it's important to know that the distance that we use is the distance, the perpendicular distance between the line of action and the point of rotation. So notice that this is 90 degrees. So if I were to have, say, a line of action this way, in other words, if this is my force, then my line of action would continue that way. My perpendicular distance is going to be this distance here. Very, very important distinction and important to know. Might run into a problem like that. So how do you draw one of these free body diagrams anyway? I mean, we keep talking about it. Let's do one. So here we have a stack of PLTW books, which I don't know who the heck uses those. So we certainly don't. We use the LMS, but somebody uses them. So we have a DE book on top. We have a POE and an IED book. Let's draw a free body diagram of the top book. So there's a recipe for drawing a free body diagram. So it's important for you to know what the recipe is. First step, sketch the isolated object. Well, what is the isolated object in this case? Well, it's the top book. And it's pretty complicated in this case. You actually draw a rectangle. Right, so then the next step is to sketch the applied, and this says norm. We really use the word normal. So sketch the applied and normal force. Normal just means, in this case, perpendicular. Not that there are abnormal forces. Normal means perpendicular. Okay, so a normal force is something that is perpendicular to the surface. So really the best explanation is to show it. So if we have our book, we have the weight of the book, and it points down, and the weight of the book is just, it is a force, and it's equal to the mass times gravitational acceleration. Okay, that is weight, something you must know for sure. That acts down. But remember, for every force we have in a direction, we have to have a force acting opposite. So when we have the force acting opposite, that is our normal force. So normal force in this case is really just the table supporting that book, or really I guess it's the POE book supporting it. So the table pushes on the IED book, which pushes on the POE book, which pushes up on the DE book. So because of that, I have two forces. Now those should be the same. There's nothing pushing from the left or right. So this force pushing up, that's called the normal force, and it is perpendicular to the surface. Next thing we want to do is we want to add some labels. Okay, so we know that the weight is 5 pounds, so we use W for weight, and we use N for normal force. Well, if we put that into practice, I mean, that was a pretty easy example. If you see, look on the lower left, these are some things that you will become comfortable with. So if we look at a very simple truss, not only do we have to add the forces, but we need to a lot of times put in lengths and distances and even some angles, because that's going to help us do the full analysis later. So that's required if the situation demands. So here's an example of a couple of kids on a sled, and I don't know if you can see it really well, but it's getting pulled by a rope here. So let's take draw a free body diagram of this and see what this looks like. All right, so to create a free body diagram, you don't have to draw a sled. Thank goodness you don't have to draw the object itself, because I'm a horrible drawer. I don't know about you. You can just draw a box. You can actually just draw a point if you want, but most people will draw a box or a circle or something like that to represent the object. So this box here represents our sled. So let's take a look a little bit deeper. So we have those kids, and they weigh something, W. We don't know what it is. We can figure that out, and it might be given, but it's W. All right, so that points down towards the earth. So represented here on the left in the real pictorial, and then in our free body diagram on the right. So if they're being pulled, they have a frictional force going to the left, which opposes that motion. So that's F sub F. They have a normal force, which we just talked about, which supports them. And then they also have an applied force. So that's the person pulling the sled. But we can't just stop there. We have to, for that applied force, define what sort of angle that applied force is going through. And that's that simple. So let's look at another one. We have this worker dude pushing, he's moving a refrigerator for you. Okay, refrigerator is here, and again, we can just draw a square, a rectangle, it doesn't matter what it is, we draw some shape to represent it. The fridge weighs something. Fridge, that weight always points down, so in our free body diagram, it points down. Take a look at the normal force. So the normal force is perpendicular to the surface of the ramp. So when we draw that in our free body diagram, we have to draw that at the same angle. Notice though that we put in the free body diagram, it's not here, just because that would make it a little bit busier. So we could draw it there. We choose to draw it here just because when we end up with our final drawing, it's going to make it a little bit neater to look at. That's all. Then we have the guy pushing up the ramp. Same thing, we're going to apply that there. And then we have frictional force opposing. What we need to do though is probably define some reference points. So I would in this case use this as my X, the applied force. I would use this as my Y, axis, and then I need to define some angles here. So then the only angle I need to define is the angle between my y-axis and the weight. So now let's look at a pulley. So we have a couple of different masses here with the pulley, mass 1 and mass 2. If we look at mass 1 first, what's that look like? Well, okay, it's just a box, no big surprise. That has a weight, weight 1, that is associated with mass 1. Weight 1 is the mass times gravity. And then we have Ft, which is, I don't know if this is a rope or a chain, doesn't matter what it is, but it's got some force. So that force is equal to Ft. The T there means it's in tension. So we're pulling on it. It's being stretched like a rubber band. And that's that simple. So if we look at the movable pulley, let's take a look at that. A little bit more complex. So here we have the weight of the mass 2, but we also have the weight of the pulley. So we can't forget that. So that pulley does weigh something, and so we have to take that into account. And then we have the tension. Key point here for something like this. So when we drew the free body diagram of mass 1, we had the tension going straight up. Important to know that the tension in this rope or chain or whatever it is, it's the same everywhere. It's the same down here by mass 1. It's the same here at the end, if you want to call it that. The tension force stays the same. Real key point. So we need to do some more definitions. So for example, when you think of a bridge or a building, they don't just float there in air, or a car. They're supported by something. You know, cars are supported by tires. Bridges have piers. They also have some supports on either side of the river or whatever they're spanning. So those are called supports. Okay, and those are reaction forces. So reaction forces could be a cable, rope, or chain, just like we saw on the previous slide. Could be a pin, roller, built-in cantilever. And you might go, well, what is all that stuff? Well, let's take a look at what all that stuff is. We already talked about the cable, rope, and chain. And in that case, you replace the force, or you represent the force in the free body diagram with tension. So here's another example. Say this maybe is a chandelier or a light that's hanging over your dining room table. Something a lot of us can relate to. So when we draw that free body diagram, we have the weight here, and then the tension force in the cable. So you can draw T, you can say, F sub T, doesn't matter as long as you have something here to represent that. Same thing if you have another example would be a sign. So a sign would typically have a cable or something else. Maybe it has some sort of bracket. But the bottom line is what that is going to look like is this. So you have the weight of that sign, you had a cable, a horizontal cable, and then you had another cable going up at an angle. And if it doesn't coincide with the y-axis like the weight, or the x-axis like A, you have to define what that angle is. So now let's take a look at some things that are probably new to us. So we're going to look at trusses. Eventually we're going to look at trusses, and we're going to look at beams. Beams are a good start to trusses. So one type of support for a beam is called a pin. So this pin is represented by a triangle, and then the line here, the other lines, represents really like the floor or the ground or something like that. And what this pin allows us to do is it allows this beam to rotate anyway. It resists motion in the X and resists motion in the Y, so I can't move it that way. I can rotate it around that point, but when we draw reaction forces there, so if we look at R sub AX, R means it's a reaction force. A means it's at location A, or pin A, joint A, and then X is the X direction. So what do you think this one might be? Well, if you said R sub AY, you would be correct. So again, R is reaction, A is the location, Y is the direction. That is the convention that we would always use and with beams and bridges. Another type of reaction is something called a roller. And in this case, this allows the beam or whatever this is to actually roll along here. So think about a board on a ball. You can roll it. Unlike the pin, which is going to resist the X and Y direction, this just resists, in this case, the Y direction. So if we were going to draw our reaction force, it's just R sub AY. So it's one reaction force. So pin was 2, a roller is 1 reaction force. So if we take a look at a free body diagram using that, so here we have a simple beam. On the left-hand side, we have a pin, and the right-hand side, we have a roller, and then we have some sort of load in the middle. Well, what does that free body diagram look like? Well, first we draw the isolated shape. We draw a force there. That could be a person standing on it, could be anything. That's our load. On the left, at A, we have a pin, so we have 2 reaction forces, and on the right, we have a ball or a roller, and we have 1 reaction force. That's it. We're done. There's some steps after that to solve the problem, but we don't have to put numbers there yet because we don't know what they are. Okay, all we have to do at this point is draw some reaction forces, and we'll calculate what those forces are later. Well, there's another kind of beam. Some of you may have heard the term cantilever or cantilever beam, and that's what's shown here. So basically you have a beam that's embedded into the wall at A, and then the green arrow here represents, some type of load. This could be a diving board. And so what we have here is something a little bit different. So if we draw our free body diagram, and we have our load out on the right, we have, it's not going to move left or right, so we have a reaction force at A in the X direction. We have a reaction force in the Y direction because it's not going to move then either. But we also add one more thing. So we add a moment at A, and one thing I want you to notice about how this is drawn, it's very important. All of these reaction forces are drawn in the positive direction. X is pointing to the right, the Y is pointing up, and the moment is counterclockwise. So that is the convention that we should draw all of our reaction forces with before we start solving the problem. You can draw them any way you'd like. That's just the convention. So quick summary of reaction supports. So if you have something that's in contact, remember normal force, remember the book, so that acts perpendicular to the surface, and remember the ramp example, so that normal force didn't go down, up and down vertically like the weight, it acted normal or perpendicular to the surface. That's why we call it a normal force. So that's contact. Cable, rope, and chain, tension. Pin, 2 forces, X and Y. Roller, 1 force, vertical. And then cantilever, you have everything except the normal force. You have X, Y, and a moment. So we're going to eventually be looking at trusses and bridges, and what does that look like? So here's a really simple one. What's the free body diagram look like for this guy? So here we have, let's pay attention, there's a pin, and we have each one of these is called nodes, so we label those. We usually use letters, so A, B, C, D, E. And over here on the right hand side we have a roller, and we have some sort of load here going down. We don't know what that is, but we know that there's 500 pounds concentrated there. So we have, what does that look like? We have, remember, a pin has 2, a vertical and a horizontal, and a ball has 1. That's it. So when we draw a free body diagram, here is what that looks like. Everything is in the positive direction. There are no moments anywhere because there is no cantilever. So the next step is to look at calculating what some of these forces are. We're going to talk about that in the next few videos.